Hey guys, what's going on? Welcome back to the fourth and final Professor Sykes video on the atomic structure and periodic table topic. Today we're going to be looking at the metals and non-metals, about group 1 elements, group 7 elements, and group 0 or group 8 elements, depending on how you look at it. So let's get started. So in the periodic table there are metals and there are non-metals. The metals generally tend to be on the left and middle sides, and the non-metals generally tend to be on the right-hand side. So on the left-hand side, and the middle as well, are metals, and these tend to be strong but malleable, so you can bend them into multiple shapes, and they won't snap. They form positive ions, because it's much easier for them to lose their valence electrons than to gain a load. And they're good conductors of electricity as well, because they have the metallic bonding means that the electrons, there is a sea of delocalized electrons, and these electrons can flow throughout the structure and carry a current. And they also have high boiling and melting points, so it will be, you need high temperatures to melt them or even to turn them into a gas. But with non-metals it's very different. Generally, non-metals tend to be dull, so they're not shiny. They're brittle, so they will snap easily. You try and bend them, they'll just snap. They have lower melting and boiling points, which is why so many of them are liquids and gases. So bromine's a liquid, oxygen's a gas, nitrogen's a gas, fluorine and chlorine are gases. You know, there's so many more gases and liquids in the non-metals than in the metals. And these generally form either minus ions, or they just share electrons and don't become ions, because it's more economic energy-wise. And transition metals are the block in the middle, so you kind of nickel, iron, cobalt, technetium, my favourite one. They're all in the middle. So these generally have some pretty fancy colours. So you can get purple ones, you can get blue ones, you can get yellow ones. When you have a metal with colours in, so long as it's not been painted to have that colour, generally that colour will have come from a transition metal in its structure. But also the transition metals make very good catalysts. So I think it's iron that's used in the Haber process to speed up the process and make it more efficient. So there are, I think, nickel's used in processes as well. So they're all good catalysts, and they have a wide range of uses beyond those that I've mentioned now. So let's look at group 1 metals. So group 1, they're all metals because they're on the leftmost side of the periodic table. They have one valence electron, and the group 1 metals are lithium, sodium, potassium, rubidium, cesium, and francium, displayed by these chemical symbols here. They generally are soft, and the softness will increase as you go down. So lithium will be the hardest of the lot, but still pretty soft because you can cut it with a knife. Francium, or francium, however you say it, I would imagine that it's so soft if you had a large chunk of it, which would be pretty dangerous, to be honest, if you did. But if you had a large chunk of it, the weight of it might kind of rip itself apart because it's so soft. They are all very reactive, in particular with the substances down here, which I'll talk about in a minute. But the reactivity increases as you go down. So lithium's the least reactive. You put it in water, you get a few bubbles because of the hydrogen forming. No one's tried putting francium in water, thank goodness. But if you put cesium in water, it will blow up the container. So unless you have a permit, don't go putting cesium in water. That's a bad idea. But the reactivity increases as you go down, and there are quite a few videos where you can watch people reacting these group 1 elements with water, which are quite interesting. So I would recommend those. Give those a watch. So when you react a group 1 metal with water, it follows this kind of basic equation down here. Obviously you'd substitute whatever you're using in. If you're not using sodium, you'd just substitute these symbols here in for that and the sodium there. But it forms the group 1 hydroxide, and it forms hydrogen gas as well. So generally be careful as well, especially if you've got other fires around in the area, if you're doing an experiment like this, which you need a license to do. So I won't be doing it on this channel. What a surprise. But if you react chlorine with sodium, which again you need a license to do, because the group 1 metals are dangerous things. But if you react sodium with chlorine, it just forms sodium chloride. And some of you might know that that is just salt. So when you react a group 1 metal with a group 7 non-metal, it just forms a salt. So even if it was potassium chloride, that's a salt. And in fact, some places do substitute sodium chloride for potassium chloride because it's apparently better for you. And oxygen is the most common reaction that you'll see in these group 1 metals. Now you might think, well, how do you do that? Do you set it on fire? You know, because setting things on fire causes vigorous oxidation, one of the two. Or what? Literally just leave it out in the air for a couple of seconds. Well, depending on which one. Lithium, if you were to kind of scratch it, it's a very shiny silver colour. But you leave it for a couple of seconds, and you'll gradually notice that a dull grey surface forms on the top. That's this stuff, lithium oxide here, forming on the surface. So it's actually corroding, not rusting. Don't say it's rusting because that's incorrect. It's corroding. And, you know, sodium, you scratch it and it will kind of form the layer of corrosion almost instantly. Potassium, you will never see the surface. You'll scratch it and as soon as you move it even like a millimetre down, it will have corroded away. You won't see the surface of that. And I wouldn't even try going and seeing the surface of rubidium. Just don't bother, you're never going to see it. Unless you keep it in an oxygen-free environment, in which case, be careful and take a gas mask. Or some oxygen mask, I mean. But you can see here as well that the reaction with oxygen isn't simple because it can either form just something oxide or it can actually form a peroxide as well, which I think would degrade down back into just a regular oxide as well. So, moving on, let's have a look at some group 7 non-metals. So these are fluorine, chlorine, bromine, iodine, and astatine. These are the symbols down here for those. These each have 7 valence electrons, so it's much more economic for them to gain the electrons or share electrons with another atom rather than to lose those, because that would require quite a lot of energy. Now, they can create covalent bonds or ionic bonds. Generally, the ionic bonds are with metals, and the covalent bonds are with non-metals. Now, the properties, the general trend properties for group 7 metals are the reverse of group 1. So, group 1 going down goes lithium, sodium, etc. Lithium is the least reactive and has the highest melting and boiling point. But francium has the lowest and is the most reactive. It's turned on its head in group 7 because fluorine at the top is the most reactive and has the lowest boiling point and melting point of them all. So it's all completely turned on its head from group 1 to group 7. Now, it's important to note that if you react any of these with a substance that has another group 1 or group 7 in the case of group 7 element in it, the more reactive one will displace the less reactive one. So if you had a solution, and it probably would be in solution because it would just form a solid salt otherwise, if you had a solution of potassium chloride and you put some fluorine gas in there, you'd have to be careful because chlorine gas is poisonous, but the fluorine would actually displace the chlorine gas, the chlorine in the potassium chloride, and so you'd actually form chlorine gas, and you can use this to kind of extract elements. So if kind of you found a load of salt and you wanted the chlorine out of it, and you had a load of fluorine that you didn't really want, you could dissolve the the sodium chloride that you found in water, and bubble the fluorine gas into the solution, and you would actually get chlorine gas from it. So let's move on to group 0 or group 8. Now, both of these are in their own way correct, but group 0 is generally the more wider used term because there are 0 electrons in their outermost shell because they filled the previous one, but they haven't got any more for the next shell. That group 0 is generally the one that we use now. But this is the most boring group of elements in the periodic table. Sorry guys, but it is. They have a full outer shell, so they're stable. The ones in this group, I should say, are helium, neon, argon, krypton, not kryptonite, just krypton, xenon, and radon. Fun fact, if you did actually manage to bond krypton with something somehow, don't know how you would, then it would be a kryptonite atom, but it doesn't bond with anything because it's boring. So because of their full outer shells, they're stable, so they're inert, they don't react with anything, they're colourless, although you can flow electricity through some of them like neon and they will glow, but on their own they're just colourless. They form single atoms, they don't bond with anything. They're not flammable, so often you can use things like helium or neon or something in to put out fires, because they won't set on fire and they'll force the oxygen out of the room, which is the thing that fire needs. So the fire just goes out because it's not got any oxygen, and it can't burn the helium because it doesn't burn. Now the trend is that the boiling and melting points get higher as they go down, which is why you kind of would use liquid helium as a coolant, and I know that they are using liquid helium as a coolant, or they will do anyway, in the fusion reactor in the south of France. That's worth researching, it's pretty cool. So that's why it's feasible to use liquid helium, because it's very cold, but it is possible to get it, and it's why they're not using liquid xenon or liquid krypton or whatever, because it's not feasible. It would take more energy than the fusion reactor would be producing to keep it a liquid. But the reason this is the case is because there are more electrons the further down you go, so there's a higher level of intermolecular forces between the atoms, because there are no bonds between them, but there are intermolecular forces. So these intermolecular forces, there are more of them, so it's harder for them to break, and so the melting and boiling points will get higher. So that is it for this video. I hope that was useful. It's a shame that we have come to the end of this topic in chemistry, but tomorrow, or whenever I do my next video, hopefully tomorrow, that would be daily upload number 5, which would be an absolute win. But tomorrow I'm not going to be doing chemistry, I'm going to be doing biology. If you'd rather I did physics, maths or geography tomorrow, let me know in the comments, because otherwise I'll just go on to biology. So that's what we'll be doing tomorrow. So I hope you found this topic helpful. Just letting you know that is over now. There are obviously still another 9 topics, so don't worry, that's not all I'm doing for chemistry. Anyway, good night and God bless.